This is the video for section 3.1 in accelerated geometry, which is on variation functions, and we're actually going to be talking about four different kinds of variation in today's lesson. So the essential question for today is, how do quantities change in relation to each other? As one thing changes, how does that affect the other things? And the essential vocabulary for this lesson, we have 5 words: combined variation, constant of variation, direct variation, inverse variation, and joint variation. So those are your 4 types of variation, as well as constant of variation. So let's begin with some vocabulary. My pen is not being helpful today. Okay. This says a special type of linear function is blank blank, a relationship between 2 variables x and y that can be written in the form y equals kx, where k is not equal to 0. So that is direct variation. So direct variation can be written in the form y equals kx, and it looks like a linear function because it is a linear function. So the word direct pretty much describes how they're related to each other. X and y are directly related to each other. What that means is that if x increases, y increases. If x decreases, y decreases. For example, if x represented the amount of time that you spend studying and y represented your grades, typically, as the amount of time you spend studying increases, your grades also increase. So in this relationship, k is known as the constant of variation. So it represents how the rates are related to each other, or how the variables, at what rate they're related to each other. And then for the equation y equals kx, we say it as y varies directly as x. So let's just look at some values that could be directly related to each other. Example 1 says, given that y varies directly as x and y equals 27 when x equals 6, write and graph the direct variation function. Okay, so we know automatically that when we see y varies directly as x, our general equation is y equals kx. And then they're going to give you some known relationship in order to be able to solve for k. So the known relationship here is that y is 27 when x is 6. So I can use that now to solve for my constant of variation k that can be used to write a general equation for this entire relationship. So to do that, I would need to divide both sides by 6, and I would end up getting 9/2, or 4.5 for k. So my direct variation equation for this scenario is that y is equal to 9/2 x. Now notice the directions also said to graph that variation function. So it is a linear function, so as long as we know the y-intercept and the slope, we can draw that line. Well, for all direct variation functions, you should always have the same y-intercept. And if you look right here, you'll notice that there's nothing there. That's because the y-intercept for all direct variation is 0. And then remember, the coefficient in front of the x is your slope of the linear function. So from my y-intercept, I could rise 9 and run 2. Or I could decrease 9 and run to the left 2. So from those points then, I can draw myself this linear function right here. And it should actually have a little arrow. And there we go. So that's the direct variation equation. So then you could use that. They could ask you, if y is 4, what is x? If x is -3, what is y? All sorts of questions based on that relationship now. One of the more common things you're going to see done in all of these variation problems is word problems. Lots and lots of word problems today. So let's try this one right here. It says the cost of an item in D varies directly as the cost of the item in dollars D. And in case you don't know, euros is the European method of currency in a lot of European countries. They share the same type of currency. And in this particular situation, E is equal to 3.85 euros, excuse me, when D is equal to $5. So find D when E equals 10 euros. So all this euros, dollars really doesn't matter to begin with. All I really need to know is that it varies directly. So instead of y equals kx, I can say E equals kd. And then once we have our general formula set up, we need to substitute in some values in order to solve for our constant of variation. So that's where the 3.85 euros and the $5 come from. When E is 3.85, D is 5. So now all you would need to do is divide the 5 over, and you get a K, a constant of variation of 0.77. So your formula is now E equals 0.77D. Now, just on a side note, what does this mean? This means that a euro is worth 0.77 of a dollar. So every dollar is only worth 77 cents, or however you want to put it, 0.77 of a euro. But that's not what they were asking us. They were asking us to find if we have 10 euros, what that would convert to in dollars. So 10 euros is equal to $0.77. Now, do you think that it's going to be more than 10 or less than $10? Well, if you're dividing by something that's less than 1, your number will increase. So $12.99 is what those 10 euros will convert to. Okay, so I want you to pause the video for a minute and give this word problem right here a try based on the perimeter of a regular dodecagon. Okay, so hopefully you set up your relationship as P equals KS, and then you substituted your initial values of a perimeter of 18 inches when your side length was 1.5 inches, and got a constant of variation of 12. So then your formula becomes that your perimeter is equal to 12 times your side length. So then they wanted you to actually find S when P was equal to 75 inches. So you just substitute 75 in for P, divide by 12, and you should get a side length of 6.25 inches. Okay, so let's look at the next type of variation. The next type of variation we're going to look at is called joint variation. Joint variation is going to occur when you have more than 2 items that are related to each other. Typically, it's 3 variables. It's a relationship among 3 variables that can be written in the form y equals k times x times z. K is still going to be your constant of variation. That's what it's going to be in all of these problems. And then for the equation y equals kxz, we say that y varies jointly as x and z. So that means that both x and z affect what y is equal to. So a situation like that would be, for example, the volume of a cone. The volume of a cone, V, varies, that should be a V there, I thought I'd change that, varies jointly as the area of the base and the height. So that means that volume is equal to some constant of variation times the area of the base and times the height of the cone. So both the area of the base and the height of the cone affect the volume, which makes logical sense if you think about it. The size of the base of the cone, that would affect how much ice cream you could put in it. The height of the cone, that would affect how much ice cream you could put in it, which would be your volume. And then we have an initial relationship that V is equal to 12 pi cubic feet when the area of the base is 9 pi square feet and the height of the cone is 4 feet. And then they want us to find B in another situation, but we don't even really need to worry about that last sentence yet. The first thing we need to do is figure out what K is by using these initial values right here. So I'm going to substitute 12 pi for my volume, 9 pi for the area of my base, and 4 for my height. So that works out to be 12 pi is equal to 36 pi times K. Then I'm going to divide by 36 pi, which is going to make my pi's cancel out, and then 12 over 36 is 1/3. So now look at this. Our volume formula is that the volume of the cone is 1/3 times the area of the base times the height. Well, you might actually remember that formula because that is the formula to find the volume of a cone. So now that we know that, we need to substitute in 24 pi for our volume and 9 feet for our height in order to find the area of the base in this particular situation. So when we do that, we get 24 pi is equal to 3 times the area of the base. So then you divide by 3 and you get that the area of the base is 8 pi. Now check your units. The height was measured in feet, the volume was measured in cubic feet. So since we're talking about the area of something, that would be in square feet. So the area of the base must be 8 pi square feet in this particular cone. So I want you to do another pause and you try on example 5 here. Take a few minutes and read through it. See if you can set it up and then solve. Okay, so if you set up, basically take that first sentence that you read through and set it up in an equation. You should have capital L is equal to K times R times the lowercase l. And then the initial situation they gave you was that capital L, the lateral surface area, is 63 pi, when the radius is 3.5 meters and the slant height is 18 meters. And for those of you who don't know, the slant height would be if you had a cone, it would be the length here of the cone, whereas the regular height of the cone would be like if you dropped a rope down inside of it from the tip down to the center of the base. Anyway, so you multiply these two things together and you actually end up getting 63, which tells you that your constant of variation is just pi. So now your general equation for the lateral surface area of a cone is that capital L is equal to pi times r times lowercase l. So then I substitute in the 8 pi for capital L and the 5 for lowercase l, and I get that in this particular situation, I need to have a radius of 8/5 of a meter, or 1.6 meters. Okay, so that's our second type of variation, joint variation. The third type that we're going to look at today is known as inverse variation. Inverse variation is a relationship between two variables x and y that can be written in the form y equals k over x, where k cannot equal 0. And for this relationship, we say that y varies inversely as x. So what it means when it says inversely is that as one thing increases, the other decreases. For example, time spent playing video games and your grade in the class. The more time you spend playing video games, the lower your grade in this class is probably going to get. That kind of thing. So let's look at just a situation with some numbers here. It says, given that y varies inversely as x and y is equal to 4 when x equals 5, write and graph the inverse variation function. So as soon as we see that it varies inversely, we know that our general equation is y equals k over x. And then the specific relationship that they've given us is that y is equal to 4 when x is 5. So we're going to use that to solve for k. In this relationship, we would need to multiply the 5 over, so k would be 20. So that means that my general equation is y equals 20 over x. This is a rational function, which is what we're actually going to spend the rest of this unit studying. So if you're not exactly sure what it looks like, I would suggest picking some x values and substituting them into here in order to plot some points. So for example, if I take 0 and substitute it in, I'm going to get undefined. That's because this has a vertical asymptote when x is equal to 0. So I know that I have this line that I can't cross. So now let's try -1 and +1. If I substitute in -1, I get -20, which won't fit on my graph. Let's try -2. -2 gives me -10. Now I'm going to think of some other numbers that are divisible by 20 just to make it easy on me. So I'm not going to use negative 3. If we use negative 4, we get negative 5. Negative 5 gives us negative 4. And then if I jump down here to negative 10, I get negative 2. So this is the first half of this inverse variation function. And that hopefully your line is a lot better curved than mine is. And then I'm going to do the same thing over here. If I substitute in positive 1, I get positive 20, which won't fit. 2 gives me 10. 4 gives me 5. 5 gives me 4. And 10 gives me 2. So I would have another curve. Over here. And hopefully your curves look a lot better than mine. So that's the basics of inverse variation. So now let's actually look at some word problems for it. Example 7 here says that the time t needed to complete a certain race varies inversely as the runner's average speed s. Okay, so I'm going to stop right there. It said that t varies inversely as s. So that whole first sentence just translates into this equation. If a runner with an average speed of 8.82 miles per hour, so this would be s, completes the race in 2.97 hours, so that would be t, what is the average speed of a runner who completes the race in 3.5 hours? So I'm going to use this first relationship to figure out k. So t is 2.97 when k is 8.82. So we would take the 8.82, multiply it over, and we actually get that k is 26.195. You can go to 2 decimals if you want to, but I did mine to 3. So my general equation now is t equals 26.195 divided by s. So now I go to this problem, which is saying that the time it took was 3.5 hours. So what was the speed, or the average speed, for this runner? So to solve this, basically the s and the 3.5 have to swap spots. So s would be equal to 26.195 divided by 3.5. So the average speed for this runner would be 7.48 miles per hour. Okay, so I want you to pause the video. I know this is a long video, but we got a lot of stuff going on in it. I want you to pause the video again, and you give number 8 a try. Okay, so hopefully at first you came up with the relationship that the time it takes to build the house is equal to k divided by v, which is the number of volunteers. Which makes sense. Those should be inversely related. The more people you have helping, the less time it should take to build the house. So then they gave you the situation that with 20 volunteers, it takes 62.5 working hours, which gives you a constant of variation of 1,250. So then your general formula is t equals 1,250 divided by v. And then they asked you what would the time be for 15 volunteers. So you just take 1,250 divided by 15, and logically the number of volunteers went down, so the amount of time it takes increases from 62.5 to 83.33 hours. Okay, one more thing we're going to look at is how can you look at a table and tell whether it's direct variation or inverse variation? So with these, you're given both the x and the y, but you don't know the k value, and you don't know whether it's a direct relationship or an inverse relationship. So this is how you can check it. It's going to be a direct variation if for every x and y combination, y divided by x is a constant. For inverses, y times x is a constant. So it's kind of backwards. If you're checking direct variation, you divide, and you should get the same thing every time you divide. If you're checking inverse, you multiply the pairs, and you should get the same thing every time you multiply. So if I'm given just a random table and I'm having to decide if it's direct or inverse, I'm just going to take each xy combination. The first thing that I would do is do 8 divided by 6.5, and I did not write this down, so let's see. 8 divided by 6.5 gives me 1.231. So then I'm going to check to see if 4 divided by 13 gives me the same thing. Well, it doesn't. It gives me 0.308. So I don't have a constant ratio here. So I know it's definitely not a direct relationship. So now I have to check inverse. So I would do 8 times 6.5, which is 52. And then I would do 4 times 13, which is 52. And then just to double check, I would do 0.5 times 104, which is also 52. So here we have a constant product. K is equal to x times y. Therefore, this is an inverse variation. Now, you try B. See if you can determine which type of relationship it is. Okay, so on that one, all of my y's divided by x's gave me a constant value of 6. So this is a direct variation. All right, last problem, I promise, and then we're done. I know this is a long video. So the last thing we have is a combined variation. Combined variation is when you have both direct and inverse relationships in the same situation. Here, for example, it says the change in temperature T of an aluminum wire varies inversely as its mass, so the mass would be in the denominator, and directly as the amount of heat energy. So since it's direct, anything that's direct is in the numerator, anything that's inverse is in the denominator. And then, of course, we can't forget our constant of variation, which can always just go in the numerator for any of these combined variation problems. Then it says the temperature of an aluminum wire with a mass of 0.1 rises 5 degrees Celsius, so that's the T, when 450 joules of heat energy are transferred, so that's the E. So when T is 5, E is 450 joules, and M is 0.1 kilograms. So I can use all of that to solve for K. And if you do, as a fraction, you should get 1 over 900 for K. So now your temperature formula is that you have your E and your M, and since it's 1 over 900, we can just put the 900 in the denominator like that. Okay, so now I can use this to finish the problem, which says how much heat energy must be transferred to an aluminum wire with a mass of 2 kilograms, 0.2, excuse me, to raise its temperature 20 degrees. So T would be 20. The question is, what does E need to be? So you would multiply 0.2 times 900, and then multiply that over here to the 20, and so you would actually need 3,600 joules of heat energy. All right, there's a lot going on. I know it's a ton of word problems. You just got to make sure that you slow down and read word for word in it.